Okie dokie. In this video, we're going to be walking through Math 1026 Lab 1, starting with our names at the top. Let's go through this as quickly as possible. So starting with cells and formulas. This is just kind of like dipping our toes into how to use Excel and type in formulas and things like that. So the idea is like if you wanted to double X values here, obviously it'd be like plugging 3 into a function of the form 2x, but let's talk about how we can do that in Excel. So basically all this stuff is saying we're going to open up Excel and type in different X values in the first column. So we're doing, what do they call it, X in cell 1. So we're gonna do, in column A, we're gonna have X values starting with 3, and then it's like 5.1, and then a -7, and so on. 7.046 or whatever it is. Nice, yeah. And then f of x in B1, so we're just labeling stuff here. And then from here, the idea is to type in the function 2x. So all you do is hit equals 2 times, not x, but you want to reference the cell. You want to reference the cell that you're doubling. So A2, you can either type A2 or you can click on A2. And then you are asked to repeat this process, right, for the other cells, because you want to find the other function values that result, from doubling these x values, right? So that's pretty much the whole idea. You can see what you've typed in this little formula box up there. So we see, 2 times A2, then 2 times A3, then 2 times A4 that we all typed in manually. So that's pretty much it. In B2, of course, it would have doubled the 3, so we got 6, and so on and so forth for the others. Let's skip around a little bit. Save your work, yada yada. So let's say instead of something basic like the doubling function, we wanted to do something more complicated, like this function here. New data set in column C, g of x in C1. So now we're doing g of x, and I believe we're just typing in that crazier function. Okay, yeah. And what formula will you type? Yeah, we'll just go ahead and do it. It's, what is it, x times x squared minus 4 to the 5th power. So anywhere we're typing x, we're going to click on A1. Okay, so it's x times, in parentheses, x squared minus 4. So again, instead of x squared, anywhere we see x, we're clicking on A2. So x squared is A2 with a caret and then a 2 minus 4. So x squared minus 4 raised to the 5th power. I know this looks crazy, but this is x times, in parentheses, x squared minus 4, close parentheses, to the 5th power. So that's that. I think that's all right here. Everything we just typed in, right? Use what you know to finish applying g of x to C3 and C4 to get those g values for the other x values, right? So we retype in this whole equation, right? It'd be this times this squared minus 4 raised to the 5th. I'm not going to do it for the next one because later on you learn that you can just click and drag this down and it'll go ahead and type that formula for you, applying to the next one. Okay, we'll talk more about that once we get there, but let's keep it going. Formula practice. So other formulas worth knowing are things like e to the x and sine of x. So like if you wanted to use e to some power, you would type equals exp and then put whatever's in the exponent spot in place of the parentheses here. Same thing with sine of x, it's just equals sine, in parentheses, the x, or whatever you're acting the sign on. So then evaluated. Okay, they're just saying, for example, to write this, they're just telling you how to use parentheses. Focus on parentheses, make sure you're doing those right. Here's some examples and what they would look like written out in Excel. What are some important features here? Always use multiplication to like split. Like you never want to type just like 3b2. You want to type 3 times b2. Use parentheses when necessary. You don't have to overuse parentheses. Like you don't have to use it around the b2. It'll be smart enough to just know to kind of keep b2 in its own little world, if that makes sense. So something like this, you want to use parentheses obviously around just the denominators, the big thing. So that's why we have just parentheses around those. Using sign here, just sin. Again, e to the something is exp, and then whatever's in the exponent spot is in the parentheses here. Anytime you're multiplying anything, even though, so like visually here, look, it's 5t, not 5 times t, but then they showed the times, which is hilarious because they did not need to show the asterisk here. But you do need to asterisk right here, right? It's 5 times t times e to the 2t. Anyway, here's the answers there. They have the answers here. I think the only difference is they did put the 10 in parentheses up top here, but again, unnecessary. You don't need to do that. Let's keep it going. Right. Okay, yeah, so in this one, all they're saying is like, if we redid the f of x, this is going back to the dragging down the formula thing I was addressing earlier. If we wanted to do 2 times the x's, right? And instead of actually physically typing in 2 times a3 and 2 times a4, all we have to do is drag this formula down. And what it does naturally is it keeps that rule. It keeps that function applying to the same like corresponding x value that's across from it, in the same way that 3 was across from this cell here and 5.1 was across from this cell here. So you don't need to manually type in functions. You can just type it in once and drag the formula down. Drag the cell down by clicking the lower right hand corner until it turns to a plus. Drag that baby down. Okay, now they give you the answers here. It's just gonna be 2 times a4. You get the idea. Let's keep it going. Great. Okay. Let's say sheet 2, getting some t values, 0 to 100.5 or 0 to 1,000.5. I'm not going to do all that. I think they just want us to do, you will enter 0 to 1.5 in column A. Okay. So we're just going to open a new sheet. In column A, we're doing what, t values, and they want us to type a 0.0 and then get all the way to 1.5. So what they would like you to do is type in equals this previous cell plus 0.5. So the step size is 0.5. And then again, all you have to do is drag this down to get to 1.5. It's going to apply whatever rule you put into it as far as you drag it down, right? So they just wanted to go from 0 to 1.5, I think. So yeah, I will say another way to go about this, they want you to use the formulas, but let's say we got rid of the formulas here. Let's say we did 0 and we just manually typed in 0.5. Well, look at this. We can already pick up on a pattern if we just highlight these two. So click on the face of this, highlight, drag down, and then you can actually click and drag these, and you can actually see the numbers, which is a better use, a better tool in my opinion, because you can't see the numbers when you use the formula, right? So you can drag it down to whatever number you want to. You could go to 1,000 if you wanted, and you'd be able to see when it hits 1,000, which is awesome. All right, so this is 0 to 1.5. Let's see what else. All right, column E. Do they want us to go back? What are we doing? Okay. Okay, drag down. So they just want us to jump to. Okay. I guess we're just randomly jumping to E. I don't know if they want us to go back. It doesn't really matter at this point, but in column E, I'm going to put T and go 4 to 5. Okay, we're going to go 4 to 5 on the T values. So starting at 4, again, you could do 4.1 and then highlight these and click and drag, or you could do what they want, and that would be click on that and then just do plus 0.1. So our step size is 0.1, and we're going from 4 to 5. So we just drag this down, and we have to kind of guess, right, until it hits 5. There it is, 5. So we have our T values from 4 to 5 going up by 0.1 in column E. Now in column F, we're going to apply 3t squared, and that's b of t. So b of t, we're doing 3t squared. So 3 times, anywhere we see t, we're going to click on this t value and then square it like so. And then this, we definitely want to drag this down to fill in the other 3t squared. Again, when you look up here at this formula, you can see that it's typing in all the correct 3t squareds for the corresponding t value. So very fascinating stuff. Let's keep it going. All right, did I do that right? F, yeah, okay. G, H, and I are going to do the other formulas. So G, we're going to apply this one here. 10 over 2 plus 4t squared. Which letter was that? F of t. So F of t going here. Again, the formula was 10 over, in parentheses, 2 plus 4t squared. All right, keep in mind, we're still using this function to act on these t values over here. So not the b values, not these function values, but still these t values that are in column E. So 10 over 2 plus 4t squared, close parentheses, just parentheses around the denominator. And then you just drag this baby down. That's all there is to it, nothing crazy. And then we can do the others. Let's see, t sine 5t plus 3, that's r. R of t, I think it was t times sine of something t plus 3. What did I say? 5t plus 3. So 5 times t plus 3. And you just drag that down. You get the idea. Let's do the last one. Just m of t, and it's 5t e to the 2t. Equals, always start with equals, 5 times t times e, which is exp, to the 2t, so 2 times e2. And just drag that corner down, fill in the other function values. Again, what this is giving us is that function, 5t e to the 2t. It's giving us like that function value for when we plug in, say, 4.7. If we plug in 4.7 to that function, this is giving us that result, okay? So that's what we're calculating. So, graphing in Excel. So then they have us just do a random formula here. Open a new spreadsheet. Okay, time from 0 to 10, and then 2 to the t. Okay, I'm just going to do another sheet. That's just easier. So I'm going to do t from, what do we do, 0 to 10. So I'm going to do my 0, 1 pattern method, and then just highlight those and drag it down to 10, just like that. And what they call it, b of t, 2 to the t. So b of t, we're going to do equals 2 to the power of t. So 2 to the power of a to the 2, or a2. And then you just drag this baby down to fill in the rest of those values. So basically 2 to the 0. 2 to the first, 2 to the 2, 2 to the 3, 2 to the 4, and so on, is all these results. So then they want us to highlight all these cells here. You can either highlight all these by starting on the T here, clicking and holding and highlighting all these, or a quick way is to just click and hold and highlight A and B here. So click on A, drag across. That's another way. Insert chart, just do this first scatter here. Let's hit a little zoom out, and naturally we have an exponential growth function. It's starting very low, it's doubling every time. So 1, 2, 4, 8, 16, 32, 64, whatever, so on and so forth. That's an exponential function. That's a graph. We have now insert a scatter plot. That is a graph in Excel. If you want to, you can get fancier with it. You can choose graphs that have like lines on them and stuff. Yeah, I don't know. I'm not going to worry about that right now. Sorry. All right. Population growth. Let's talk about a constant growth rate. Constant growth rate, that's just a fancy word for constant slope, constant rate of change, a linear function. You know, if you have a same or constant slope the entire time, that's a linear function, right? Yeah, so they give us this example. They say a certain town had a population of 1,000 in 2010. 1,000 in 2010, and then only grew by 50 people every year. So it was a locked-in rate, a constant growth rate of 50 people every year. So it'd be 1,000, and then it'd be 1,050, and then it'd be 1,100, and then it'd be 1,150, and so on and so forth. So they're saying, what should the initial condition be if it's starting in 2010? So what they're saying is t is the number of years after 2010. So really, when t equals 0, you're talking about the year 2010. When t equals 1, you're talking about the year 2011. All right, so the initial population, p of 0, is 1,000. Then they ask, what's the population growth? What is the rate of change every year? Well, they tell us that it's growing by 50 people every year. So the population growth, 50 people per year. That's the units, it's people per year. A rate of change is typically like the y units, the y value units on top, x value units on the bottom. So it's like population over time, people per year. So next one, what's the differential equation? That's just a really aggressively fancy phrase for, p prime. So p prime is just the derivative. A derivative of a function that's constant, or something that has a constant rate of change, is just going to be that constant rate of change. Like p prime is the derivative, which is the rate of change, which is a constant 50. So like these two questions are the exact same, just asked differently, right? So if p prime is equal to 50, now they're asking us to basically find the antiderivative and find p of t. Now, this is easier said than done. They say, what kind of polynomials have a constant derivative? What they're trying to say is like, think of a function for which if you take its derivative, you just get 50. Well, that is just going to be 50t. And then plus the initial condition, p of 0 equals 1,000, that's basically going to be our y-intercept, right? So what we're constructing basically is not a 50th anniversary. It's a, a y equals mx plus b function. So the idea is like we have our slope, our rate of change, our constant rate of change, constant growth rate of 50. But then this was the population at the very beginning. So like the growth rate doesn't really play into this 1,000. So it's almost like those problems where it's like there's a starting fee, and then for every hour you charge this much money or something. It's kind of like that, but it's like 1,000's the base number, and then plus 50 for every additional year. Does that kind of make sense? I don't know. Hope so. Open a new spreadsheet. We're going to do t values in A2, so time in A2, and then we're just going to apply this function, this mx plus b, this linear equation in B. Okay. And we're going to call it, what are we going to call it? Constant growth rate. Okay, so you can like double click, you can type whatever you want. Growth rate. Okay, so we have t values, we have, I don't know what we call it, just constant growth rate. Population. Okay, yeah, we'll just call it pop. Population. So we have the t values from 0 to 20. So I'll do 0, 1, highlight it all the way to 20. Again, at time 0, that's talking about the year 2010. By the time we get to 20, it's 2030. All right. Population. We're going to type in the function that we just came up with, which is 50t plus 1,000. So equals 50 times t, so this, plus 1,000. So we just click and drag this baby down. Literally all this is doing is adding 50 every time, right? Because all this function is it's starting at 1,000 and it's just going to add 50, every year. So it's just going up by 50 until it hits 2,000 in the year 2030, 20 years after the start, which started at 2010. How many years will it take for the population to double? Well, just like we said, population starts at 1,000. So it doubles when it reaches 2,000, which happens 20 years after the start, which is the year 2030. Okay, so I typed that answer in wrong. So it's 20 years is what they're asking, but if they asked what year, it'd be 2030. So they say, intuitively speaking, if 1,000 people give birth to 50 babies per year. One would expect 2,000 people to give birth to 100 babies per year. Yeah, that's realistic, but they ask you to kind of do a thought experiment and say, you know, can you think of a reason why the growth rate doesn't rise as the population rises? Maybe the town they live in only limits their, you know, they have a limit on how many births can occur every year, and maybe it's 50. Maybe people are dying off. Does that even make sense? Not really. I don't know. Let's go with the town has a law where 50 babies is the max. Okay, that's pretty much it. So they're just saying at the end here, a more real life scenario would be more of an exponential growth scenario as opposed to a constant growth rate. So now, getting into an exponential growth scenario, they say, suppose y, so they're talking about directly proportional first. So if y is directly proportional to x, that means that y is equal to k times x for some constant k. So if you have a population model for which the growth rate is directly proportional to the population size, that means the p prime, the rate of change, is equal to some constant times the actual population. Then if you solve this differential equation, in other words solve for p, you end up getting the initial population, so p of 0, times e to the at. If you've seen the equation PERT before, like a equals pe to the rt, it's the same exact equation. So they say something about like verify this is the solution to this equation. All that means is like if you took the derivative of this, if you took the derivative of p to find p prime, would you get this here, a times p of t? And you would, because when you look at this function here, the derivative of e to the at would be the same thing. It'd be e to the at times a. So we'd have to use the chain rule, right? So the derivative of e to the at is e to the at, and then the derivative of the exponent, the inside layer, is a, and then this constant, this coefficient, p of 0, would just stay out in front. So p prime would be equal to p of 0 times e to the at times a. Well, p of 0, e to the at is really just p of t. So it'd be p of t times a. P of t times a is p prime. That's the verification. I hope that made any sense without me writing it out. Regardless, it doesn't really matter. We're going to talk about in Excel how to use this equation to get the accurate model of bacteria growth. So we're going to make a equal to 1, so our like rate in the exponent there is just going to be 1. In a new worksheet, we're going to call it exponential growth. Double click exponential growth, and we are inputting time 0 and the population of 1. Okay, so they tell us at the top to put time over here, t-value starting at 0 and going up by every hour, and they want us to have a step size of 1 hour, but they want the span ultimately to be over 5 days. So 24 hours in a day, 5 days, 5 times 24, it's 120. So we're going to go all the way to 120, highlighting those 3 cells and dragging down until we get 120. So we have all the time there. Now, I guess just population in the next column. Bacterial population. Bacterial pop. So now we're just inputting the equation. We're inputting this formula, p of 0, e to the at, and for p of 0, we're going to use 1. So p of 0 equals 1 right here. And then a is also equal to 1. So it's going to be very easy for us. So p of 0 is 1 times e to the at. So again, a is 1 times t, which is the 0. So click on the 0 to reference it, so that when, like, once you've typed in this formula here, you can click and drag this down. And what it's going to do is spell out all the other bacterial population values for these corresponding hours. Okay? Then there's something about mass. They give us that the mass of a single bacterium is 1 times 10 to the negative 12. And then they want us to like find the mass of the entire population at any one time. So like the mass of the entire population at the very start is just going to be the mass of a single bacteria because it just starts at 1, right? So we're basically going to set up a formula to say that the population mass is just going to be the population times the mass of a single bacterium, which is 1 times 10 to the negative 12. So you could say 1 times 10 to the negative 12. So it's taking the population at any time and multiplying it by the mass of a single bacterium. And then from there, we can click and drag this down. And what it's doing, again, is multiplying the mass of one bacterium times the number of bacteria, and it's giving us the mass of the entire population. So eventually they ask, determine how many years must elapse before the colony's mass is greater than the mass of the Earth. And they told us that the mass of the Earth is 6 times 10 to the 26. So basically we need to find when does this population mass surpass 6 times 10 to the 26. So we can start seeing these numbers rise. I hope it's clear that E plus 11, E plus 12, that means 2.09 times 10 to the 12th. This means 4.2 times 10 to the 13th. So we want 10 to the 26th. So we're scrolling through. We see 10 to the 26th here. 1.65 is not as big as 6. We want something greater than 6 times 10 to the 26. Again, 4.48, not as big as 6. So the next best thing is 1.22 times 10 to the 27. That's the next hour for which it'll actually surpass that amount of 6 times 10 to the 26. So the number of hours is 90 hours. And they tell us that in the next statement here. They say 90 hours, it's 1.22 times 10 to the 27. That's exactly what we found. Fortunately, we don't have to contend with continent-sized super colonies of bacteria. What do you think is the most significant factor preventing the formation of giant colonies of bacteria? This is, again, where you can just be creative, just come up with something. Maybe Lysol, maybe hand sanitizer. We don't have bacteria because we can clean stuff now. We have, medicine, whatever. Lysol's a pretty good answer. That's kind of funny. Okay, that about wraps it up. I hope this helps on Lab 1. I'm about to call it here. Thanks for watching. Hope this helped. Bye-bye.